Good afternoon, everyone, and welcome to another joint EOL-RAL seminar. It is my pleasure to introduce our speaker, Dr. Gijs de Boer, who is a research scientist at CIRES in Colorado University and at NOAA's Physical Sciences Lab here in Boulder. Gijs is well known in the Atmospheric Science Department at the University of Wisconsin-Madison, where he received both his master's and PhD. Currently at Colorado University, Dr. de Boer is the chief scientist of the Integrated Remote and In Situ Sensing Group, where his research focus is in the high latitude environments, studying applications of unmanned aircraft systems for atmospheric research, aerosol cloud interactions in Arctic clouds, and process studies in Arctic cloud formation and life cycle. With his interest in the Arctic atmosphere, it is no surprise that Gijs is on the International Arctic Science Committee as our National Academies of Sciences US delegate, among other committees that focus on atmospheric science in the high latitude environment. His latest paper was published in the Bulletin of American Meteorological Society on the capabilities and development of unmanned aircraft to study the atmosphere. And this leads us to his seminar, topic entitled Robotic Revolution, Recent Work in Earth System Observing with Remotely Piloted Aircraft. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your question pop up. We are archiving all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. Gijs de Boer, we welcome you to EOL and RAL, and the virtual stage is now yours.
Great, thank you. I'm muting and starting video here. Thanks very much for the wonderful introduction, Jackie. I appreciate that. And thanks everybody for being here. It's really great to be able to present to the NCAR community, and it's unfortunate, of course, we can't do it in person, but I'm happy and excited to share some of our recent work. As was mentioned in the introduction, I wear a lot of different hats, primarily at the University of Colorado. I will say quickly, one hat that I wear that wasn't mentioned, but is represented in the bottom right there, is that I'm founder of a small consulting firm called Boreas Consulting. And the reason I bring that up is because one of the companies that I've worked with in that capacity is Black Swift Technologies, who are here in Boulder. And you'll see their name in the presentation. I think I provide that information in an unbiased way, but just from the perspective of full disclosure, I wanted to make sure that everyone is aware of the work that I've done with them in the past. So to get started here, I wanted to start with just a little bit of background on my research history. As was mentioned in the introduction, I've been focused on high latitude environments for quite some time now, since my time in graduate school. And one of the things that I spent a lot of time trying to understand was the kind of dynamics and physics of mixed phase stratiform clouds in high latitude environments. And it was about 10 years ago that I was working with colleagues at NCAR and NOAA and elsewhere to develop a review paper for Nature Geoscience that talked about the really complex web of interactions that come together to support the life cycle of these types of clouds. And in the process, we were developing these nice figures like the one that's on the screen here, and really trying to document our state of knowledge and the things that we knew and we didn't know. And in doing so, it became really clear to me that we didn't necessarily have all of the perspectives that we needed to fully address the questions we might have about these clouds and what makes them tick. And so looking at some of the really important processes and physics of the situation, thinking about the thermodynamic structure of the lower atmosphere and its evolution, which we were used to having radiosondes every 6 or 12 hours if we were lucky, and trying to guess at what was going on in between. Things like the dynamics of the cloud and the turbulence generated by the cloud layer, where we had some limited remotely sensed measurements, but not nearly enough to really close in all the gaps. Information on the precipitation the radiation and the radiative structure of the clouds, the spatial variability of the near surface, turbulent fluxes and other terms of the surface energy budget, like albedo, for example. And perhaps one of the more important ones is the vertical structure of aerosol particles that can impact the microphysics of these clouds. And so it was in that thinking state that I started to stumble upon other ways in which we might observe the atmosphere. And while I don't remember exactly all of the steps that led to this, I think one day I was thinking about how cool it would be if we could just instrument some birds that were up there anyway, because some of the other assets that we had available to us, like large research aircraft, just weren't necessarily practical, both from a cost perspective, as well as from the perspective of flying in what could be a fairly dangerous environment in icing conditions at low altitude. And that's kind of where my thinking started moving towards drones or uncrewed aircraft systems, which is what the rest of this presentation will be about. Just to start with a bit of a definition here, when you say the word drones, a lot of different people have different thoughts on what that means. And I'm sure even in this audience, people have a pretty good perspective on the sorts of platforms we might be talking about, but there's a huge range of different platforms. And you see in the top image there, that's me, all 6'4" of me in front of the NASA Global Hawk, which is a very large aircraft, one that NCAR is quite familiar with due to instrumentation that's been developed for that platform. That's an aircraft, of course, that's kind of on one extreme on the high altitude, long endurance side of things. Not necessarily the best platform for detailed studies of the boundary layer. And on the other end, we have these kind of consumer drones that are commonly available. I'm guessing some of you have these types of systems that are quite light and small and compact and easy to fly, like the DJI system that's in the bottom picture there. Those also have their place, but not necessarily exactly what we're looking for with respect to being able to instrument them with a variety of different sensors and types of packages to help us understand the atmosphere. And so the presentation here focuses on what are called small UAS. These are typically on the scale of, a half meter to a couple meters in size, both including fixed wing and multi-rotor platforms, and are by definition in the weight class between about 0.55 and 55 pounds. So that's really going to be the focus of what I'm talking about today, is that scale of platform. And those platforms have some very distinct advantages. For example, they have a very small operational footprint. This is a video of us launching one of our Raven systems off of a beach in Barbados, because we were there to study clouds. I'll talk more about that later. But you can see that it doesn't take much space or many people to operate these aircraft. I'll let that video go one more time. You can see here we're using a bungee launcher and a tent to house our laptop and equipment. That makes them easy to deploy in a variety of areas. It makes them quite transportable. It also means that they're relatively inexpensive to operate, and what relatively inexpensive means is different to different people as well. But I would argue that for the amount of data that you can collect with one of these systems, the time in the field is relatively inexpensive. They're also highly portable. I mentioned that earlier. Here's an example of us launching one of these systems off the top of the tracker vehicles that CIRES has for specifically this purpose. They're also great outreach tools, and you can see the guy giving the thumbs up there with the beer shirt on. I should tell him not to wear that next time. He's an undergraduate student that was deployed with us at this particular campaign. These platforms are really great for engaging students, for engaging early career scientists, and for engaging the general public. They tend to captivate people's imagination and provide pathways for discussions on what it is we're doing. In addition to those things, these platforms are also nice from the perspective that they're relatively slow flying. And this is onboard camera from a Raven flying over coastal Wisconsin. We operate this platform between approximately 15 to 20 meters per second, sometimes a little faster if there's high wind environments. And some people might see that as a disadvantage, but quite frankly, for us, it provides us an opportunity to get much higher resolution measurements of the phenomena of interest. And so when you're flying at this sort of a velocity with sensors that have a high response time, you get down to centimeter scales, which can be really nice and something that's really difficult to achieve through other means. And then finally, the thing I'll say about these types of platforms, I mentioned earlier that we didn't necessarily like to fly people into some types of environments. This is video of one of the other IRIS aircraft flying in severe weather in the Midwest, trying to understand the dynamics of the rear flank of the supercell. And clearly, there are places where we don't want to put people's lives at risk. That would be most places. Or any places. And so these types of platforms can be operated safely in high risk environments with some planning. And so they offer opportunities to make measurements in places where we otherwise wouldn't necessarily be able to send airborne platforms for in situ sensing. I wish I could tell you that I was the first person to think of all this. Clearly, I wasn't. There were many people before me that started to leverage small UAS for atmospheric research, and I just have a few examples here on the screen. As an aside, I'll say I'm happy to have all these pictures be black and white because it makes it look really old. But some of this stuff wasn't too long ago in the 80s and 90s, where people started leveraging these types of platforms and instrumenting them to understand things like thermodynamic structure and turbulence in the lower atmosphere. Having said that, we are in the process of what I consider to be a bit of a revolution. I think it's the golden age of miniaturization. We have, computers in our pockets with our cell phones. We have sensors. I'm wearing a watch right now that can tell me everything I want to know about how well my run went earlier today. So we have a lot of technological advancement that is pushing us in the direction of greater capabilities with small things. And so we stand to benefit from that from the perspective of small UAS, because people have been working hard to develop new sensor systems, new autopilot systems, new communication systems, et cetera, that all can be leveraged for this type of research. And so with this backdrop, I was fortunate in that when I started my position here at the University of Colorado about 10 years ago, the timing was right, I would say, to jump into some of this type of research. And the environment was great as well. And I would be doing a lot of people a disservice if I didn't recognize the fact that the work that I'm going to show in the rest of this presentation is the result of collaborations with a wide variety of people, the Boulder contingent of which is kind of pictured here. You probably see some familiar faces from NCARB as well as from other areas. And we've had support from a variety of funding agencies and institutions to help develop some of these tools and techniques. And I think we're just scratching the surface. There's a lot more that can be done there. So jumping into the early campaigns, I think I was excited. I had an Arctic research background, and I decided that the best place to start doing this would be in the Arctic. And there were reasons to think that would be true. One is that the Department of Energy had just stood up a new observational site at a place called Elliptic Point on the north slope of Alaska, a little bit east, of Utqiagvik, which is formerly known as Barrow. Elliptic Point has with it restricted airspace, both directly over the site and a warning area that extends far offshore. And so from the perspective of regulations and interactions with the FAA, this was very easy. Of course, that comes along with interacting with DOE to demonstrate all the safety issues there. But we took our platforms as part of a campaign called Erasmus. That was kind of the first proposed campaign to the North Slope in 2015, and learned a lot, frankly. We did a lot of flying. You can see the statistics on flight hours and number of flights on the right-hand side there. Our flights ranged between April and October, typically. We didn't really fly in the winter season in the dark, but learned a lot about flying in harsh environments, about icing, about operating near bears, working in the vicinity of a strong Air Force radar, a lot of lessons learned. From a scientific perspective, you see the 3 questions in the bottom right here with respect to low-level temperature and moisture structure and their relationship to clouds, the vertical structure of aerosol properties, and the performance of our remote sensing retrievals. Those are the things that we proposed to go after. And I think this work was successful in the sense that it did address some of these questions. It also helped to facilitate the adoption of this sort of technology within the Department of Energy's ARM program. And that continues today, although maybe not in the same form that we introduced it. So just a few examples of the sorts of measurements we were making, thinking specifically about the Arctic boundary layer structure or lower atmospheric structure. Here's a nice example of a crisp, clear October day, right as the sea ice is starting to freeze up. You can see in the top left, this is an image from aboard the Data Hawk as we were flying over the runway at Aliktuk Point. We had a very strong near surface temperature inversion. And just as an introduction to the Data Hawk itself, the picture on the top right shows the platform and the sensors that we carry on board. This includes an autopilot system developed at the University of Colorado, along with a fine wire array that was developed at CU, and then some sensors to sense pressure, temperature, and humidity. In this case, it's a Vizsla sensor. It hasn't always been a Vizsla sensor. We've also flown sensors from IMET and other companies. But for this particular day, the bottom figure shows the sampling that we were doing. And you can see we were very focused on the layer between about, let's call it 30 and 150 meters or 200 meters, where we saw these really strong temperature inversions in place. We did also conduct a couple of low altitude flights. You can see here and here, assuming you can see my mouse, just after 9 and right around midnight. Those were geared at looking at near surface fluxes. So we're flying at 20 meters, in this case, right over the sea ice. From an evolution perspective, the next day was quite different. We had low cloud cover, and you can see the thermodynamic structure evolved quite dramatically. We had now a warming surface, or a warm surface from the presence of the cloud, and additional wind, which created a shear-driven mixed layer near the surface. And we had a cloud-driven mixed layer aloft with the remnants of that inversion here. And so this is the sort of documentation that we were hoping to accomplish to evaluate whether modeling tools can get some of these types of transitions correct, or whether they might want to mix out the entire lower atmosphere with the presence of a cloud. And these are questions we're still working to answer, and I don't have answers to right now, but these data support those types of analyses. Switching gears just a little bit, a few years ago, there was a nice paper that Peter Sullivan and co-authors put together looking at the structure of stable boundary layers. And in that modeling study, it was found that there were these temperature fronts that came through the domain where we had these random kind of mixed turbulent structures that kind of processed through in time. And so we were curious for the cases where we had these nice stable boundary layer conditions, whether we were able to see similar structures. And sure enough, on analysis, this is just an example from one of the flights that I showed you in the previous figure. You can see very clearly these well-mixed structures that are vecting through. And so currently, Brian Butterworth, who is a research scientist working with my team here at the NOAA Physical Sciences Laboratory, is digging into these cases in more detail to better understand what drives these structures and drives their evolution. And at first glimpse, it looks like there are strong connections to the presence of a low-level jet and the kind of shear layer that develops at the interface of that low-level jet. I talked about aerosol properties earlier, and we were, again, fortunate to be co-housed with our collaborators in the Chemical Sciences Laboratory at NOAA. And they had just been working to develop a small aerosol optical spectrometer called the POPS. And this is an instrument that we flew back in 2015 as part of Erasmus to get detailed profiles of the lower atmosphere. This figure on the bottom left provides an example of those types of profiles. And you can see the structure that exists with a local maximum around 250 meters in this particular case. And we leverage these types of data for our flying activities on the North Slope. This sensor has since been picked up by the Department of Energy, the ARM program, and they've been flying it on their tethered balloon system as well as on their other aircraft. And finally, I mentioned retrievals, and these are some examples of how our electronic data were used in that sense. So we have this top figure showing the measured temperature structure of the atmosphere relative to retrievals from remote sensors, in this case, an ARRI system that was at the North Slope, where the colors are the same at the same altitude. The system was performing well. Where they're a little bit different, you can see there are issues. Like at the end here, for example, you can see that the system was recording slightly warmer temperatures, or excuse me, colder temperatures than what was actually measured. And we've done similar analyses as model output, in this case with a fully coupled ice ocean atmosphere model that was running in a weather forecasting predictive capability. Through some of this early work, I also became entrained in a community that's known as ISARA. This is the International Society for Atmospheric Research Using Remotely Piloted Aircraft. I'm guessing some of you are familiar with this society already. It's a fantastic group that is exclusively focused on using these types of platforms for atmospheric science. And I was fortunate that in 2018, I was selected to be the science chair for this group, and we were able to bring the meeting, the annual meeting of the team, to Boulder, and we brought about 150 of the best scientists in this area and engineers as well to the Boulder area, both to have a great meeting and discussion, but equally importantly, the week following the meeting, we had what we called a community activity, a flight week, which we termed lapse rate, which is lower atmospheric profiling studies at elevation, a remotely piloted aircraft team experiment. And we took aircraft that were operated by teams from a variety of US institutions, including Virginia Tech, Oklahoma State, University of Oklahoma, University of Nebraska, University of Colorado, of course, and Blacksmith Technologies, out into the field. And we flew the wings off of these platforms. And I say that largely figuratively. There might have been one wing that actually came off at one point, but we flew over 1,000 flight hours in about 4.5 days, which was a lot of flying to be taken over that amount of time. And we did this in the San Luis Valley of South Central Colorado. The map shows our flight locations on the different days, and the imagery just shows kind of the scene down there. And we flew with a few specific, loosely organized objectives related to the AM boundary layer transition, aerosol properties in the valley, drainage flows, and convective initiation. And so just a few examples of the sorts of things that we looked at. When it comes to drainage flows, there are some smaller valleys that feed in the San Luis Valley. And we operated aircraft, particularly the last day of sampling, we were very focused on that specific topic, looking at the kinematic and thermodynamic structure of the drainage flow so that we can test some of these kind of 1D and 2D models of what that flow might look like. This next slide shows some examples of the measurements that we collected during the campaign. And I won't get into all of the details here because there's a lot going on, but generally it shows some nice perspectives on the sorts of analyses we can do. On the bottom left there, you have the theta V evolution over time, of course, with the drainage flow in place initially and then converting to a well-mixed lower atmosphere. The bottom right shows some of the spatial information that we can collect with the platforms, not just in the vertical plane, but also horizontally. And so this vertical axis in these figures is actually the distance across the canyon, so across the valley in the Saguache Valley, which is in the upper left here. You can see this narrower valley that extends into the San Luis Valley. And here you get to some of the details on how the horizontal structure of this flow changes over time, as well as over the width of the valley. We also worked with our colleagues at NCAR, with Anders Jensen and James Pinto, to investigate how well these observations might be used to inform forecasting or prediction activities. Specifically here, we looked at how integrating observations from the UAS might help to support improved prediction of the drainage flow. And so you can see on the left-hand side here at two different altitudes, 13 meters on the left column and 116 meters on the right column, the change in the predicted flow probability, where we have, without any sort of assimilation of either the surface observations or the UAS observations in the top panel, the UAS observations alone in the second panels, the surface observations alone in the third panels, and then the combined UAS and surface. And you can see a much higher probability of that drainage flow setting up in the simulations where the UAS observations were integrated. And that bears through in this right-hand comparison as well, where we have LiDAR data to compare to, and you can see that without bringing the UAS in, the model was not really able to set up any sort of stronger drainage flow in this area. Another thing that we did during lapse rate was a lot of system intercomparison, and this was a primary objective where we had some surface-based instrumentation, including remote sensors and tower-mounted instruments that we can compare our UAS-based observations to. This is all documented in a paper by Lindsay Barbieri from 2019, but it showed some interesting things. It showed, one, that the integration is really, really important. And I think we knew this, but this kind of is a nice way to document that even when we're using the same sensors, the way that those sensors are integrated into platforms becomes a critical component of how well that sensor performs. But it also showed that largely our systems were providing research grade measurements and were able to be used for this sort of atmospheric science that we were talking about here. As a result of this, though, I got an idea and an ambition to try to develop a standalone sensor system that I called Miniflux. And this is combining instrumentation to measure thermodynamic state of the atmosphere, winds, and turbulent fluxes from a package that's about 450 grams and a few inches by a few inches. And the purpose of this, or the idea behind it, was that this sort of a payload could be then integrated onto a variety of different aircraft in roughly the same way and provide consistent observations. And a few examples of that being deployed to the field. I'm cheating a little bit here because some of these aircraft are not small UAS. For example, the Sea Hunter, which is a twin engine aircraft that we deployed in Northern Alaska in collaboration with the University of Alaska Fairbanks as part of the stratified ocean dynamics of the Arctic campaign that ONR supported a couple of years ago. You can see Miniflux installed under the nose of the aircraft here. And the purpose of this campaign was to collect detailed measurements of the lower atmosphere between, maybe 500 feet and 6,000 feet between the Alaskan coastline, over the landfast ice, and then out to the marginal ice zone a couple hundred nautical miles offshore. There were also surface-based assets in place for the campaign. You can see a few different measurement examples. In this case, one of the kind of complex temperature structures that we observed in this Arctic environment, and some of the response of, for example, our temperature sensors going to 50 hertz here. We get very nice response in a well-mixed environment. Lately, we've been working with NOAA, and this is actually a small UAS platform that is designed to be able to take off and land vertically. So it's a hybrid aircraft that has a hexacopter or a quadcopter style of electric takeoff, and then transitions to horizontal flight. And here we have Miniflux under the wing. The idea here being that we can deploy this aircraft from ships in remote ocean environments. And it's, in my opinion, one of the only ways that we will regularly be able to get observations near the surface over remote ocean environments, just because there aren't many assets that can get out there and stay out there and are willing to do extensive sampling down, between the surface and 1 kilometer, for example. The bottom figures just show some examples of data from this particular set of flights that were conducted in the Arizona desert last spring. You can see a boundary layer transition sort of environment as the day evolves, a significant amount of turbulence building and variable wind conditions. The other thing that we did with the Miniflux instrumentation is further one of our own platforms at the University of Colorado, this platform being the Raven, which is pictured here. You can see that a lot of the components from the Miniflux are now integrated into the Raven, distributed on the airframe a little bit, which is slightly counter to what the idea of Miniflux was supposed to represent. But we did become aware of the fact that having one body wasn't always the most efficient way to do things. And so we were comfortable redistributing those sensors in a way that we could characterize them carefully and then deploy them for scientific reasons. Again, you can see there's a multi-hole probe on the nose to measure angle of attack and side slip. We have that fine wire array that I talked about on the DataHawk as well. We have up and downward looking IR sensors to give us information on the presence of clouds overhead or surface structure variability, coastlines, ponds, etc. And then again, looking at pressure, temperature, humidity sensors up on top of the body here. We have 2 Weisslar SS421s paired in an offsetting angle so that we don't have hopefully solar effects on those. As a quick aside, you see the little cartoon on the right here. This is something that was developed for a current campaign called Splash. And I'll talk a little bit more about Splash in a minute, but again, trying to connect to ways that we can engage a variety of audiences, we decided to design superheroes around some of our instruments. And so Winged Wonder was born. Last spring, we took the Raven out to the Southern Great Plains facility in Oklahoma. Additionally, we flew at the NREL Flatirons campus here in Boulder to do comparisons against tower-mounted instrumentation. And so the plots on the left are time series of Raven wind speed and direction observations in the red curves relative to those from both cup style anemometers and sonic anemometers that were mounted at the same altitude. You can see that generally things agree quite well between the two different platforms, or between the Raven and the tower mounted instrumentation. On the right is a slightly different type of comparison. Here we were doing repeated chasing of radiosondes in the lower atmosphere at the SGP facility. We also compare to the tower there, but I'm just showing figures from the radiosonde comparison. So the radiosonde would be launched and we would profile up behind the radiosonde a few seconds afterward. And you can see now comparisons for a variety of aircraft, the Raven being kind of the mustard yellow points, but we were also there with the Black Swift S2, the University of Oklahoma copter sonde, the University of Nebraska operated Meteo drone, and another M600 platform that the University of Nebraska brought along. So generally, these platforms agree well with what was being measured by the radiosonde, with some scatter around that one-to-one line. With that sort of characterization, we felt comfortable bringing this into more of a research environment. And one of the recent campaigns that we participated in was the Atomic campaign. This is the campaign in Barbados that I was referring to earlier. And the primary objectives for Atomic were really focused on understanding convective mass flux, mesoscale organization, and depth of the shallow fair weather cumulus clouds or trade wind cumulus clouds that develop over the tropical Atlantic. They're very important from a climatic perspective because of their ability to both redistribute moisture and heat through the atmosphere, as well as just their impact on the local surface or local planetary albedo, with the cloud cover, of course, being much brighter than the surface ocean, as well as understanding, the structure of the boundary layer and how that evolves with cloud cover. And so our primary objective for Atomic, and this was actually a campaign that we deployed on very short notice for, because originally we were supposed to take the hybrid platform that I was talking about developing with NOAA and fly that off of the Ronald Brown offshore. But unfortunately, the aircraft was not quite ready to go. And so with about a month and a half notice, we mobilized the University of Colorado team to get the Raven to operate in the nearshore environment. And so we were housed on the beach in Morgan Lewis here in the northeast corner of Barbados. All of our flight activities were in the nearshore environment, extending a couple of kilometers offshore. And we did very regular type of flight patterns that we repeated twice a day, almost every day that we were out there. Overall, we got about 87, I think, flight hours out of this campaign over the course of about a month. And that profile looked a lot like what you see here, represented by this one flight, where we would conduct an initial profile up to 1 kilometer and then do extended legs at a variety of altitudes. The first one being right below cloud base, which is what you're seeing in the video there, and then stepping down to 400 meters, 200 meters, and 20 meters so that we can collect statistics at those altitudes over time and be able to start to piece together flux profiles. So just some examples. This is a summary of the thermodynamic structure measurements that we made. You can see the top half of this figure are the Raven data. And so the bottom is from ocean-bound systems. You can feel free to ignore those, but this provides a nice complete picture of how the pieces fit together. And here you can see very nicely, the sort of structure that we were observing associated with these types of cloudy conditions over the course of the month. Looking at detail, you can see some of the scatter that occurs when we held altitude for a while. And so you do see some of this local variability. And one of the questions that we wanted to address is how that variability changes with height in the subcloud layer under these types of marine cumulus clouds. And the figure on the right shows just an example of that sort of a question where we're looking at distributions of the temperature anomaly from the mean temperature at both 20 meters, so right above the water surface, as well as up at 500 meters. And this is something that we're planning to extend to, of course, more than one flight, but this is one of the sorts of the examples of the type of information we're hoping to pull out of these measurements. Similarly, we looked at vertical velocity structure. And so another example of looking at vertical velocity at 500 meters versus 200 meters, both in clear conditions, and then adding in the conditions where we had a cloud overhead. You can see the skewness of the distribution changes pretty dramatically with the cloud in place. Again, more to be done here, but some nice insight into the dynamics of the subcloud environment. And then looking at stress near the surface as a function of the surface wind speed from the Raven from our flights at 20 meters above the surface. And this is work that's in prep for publication in a paper that's really looking at the momentum budget. One of the benefits of using the UAS, of course, is being able to get profiles. And so we're trying to piece together the momentum flux profiles through the subcloud layer here for different wind regimes, which is why we color coded by dates here. Shifting gears completely, another recent campaign that we were involved with was Mosaic. This is the multidisciplinary drifting observatory for the study of Arctic climate. And this is a campaign that took place from September of 2019 to approximately October of 2020. For those not familiar with Mosaic, the research vessel Polar Stern was frozen into the sea ice here at 85 north and allowed to drift over the course of a year. The colors in the map here are different legs from the expedition, the blue being the first legs 1 and 2, the kind of salmony colors leg 3, the orange colors leg 4, and then the purple leg 5. If you wonder about this discontinuity, it's because the ship got spit out of the ice pack here in the summer. And so they repositioned back near the North Pole for the last bit of leg 5. And our UAS team was specifically targeting a few different hypotheses that you can see on the right here, specific to the complex structure of the Arctic boundary layer and the ability of models to represent that based on their own parameterizations and vertical resolution. The impact of leads and on the transfer of energy into the atmosphere, and how well, again, models are able to capture that sort of energy transfer. And then the subgrid scale variability that exists in the coupled Arctic system. And this is as much focused on the surface as it is on the atmosphere. So our part of this mission took place on legs 3 and 4. Legs did get shuffled around a little bit due to COVID, but you can see where we were flying. The green dots represent places that we flew the Data Hawk, and the Data Hawk was flown from the ice surface in this case. And the red dots represent times where we were flying the Helix. I'll talk more about that platform in a second, but that's a multi-copter platform that was mainly looking at radiative terms. And so you can see we operated as high as about 87 degrees north, and as you'll see in a second, at fairly cold temperatures. So getting to the complex structure part of this question, this is Mosaic in a nutshell from the Data Hawk's perspective. You can see we sampled a wide variety of thermodynamic conditions from very early on in the campaign, where we were operating at minus 30 or so near the surface, to late in the campaign in the summertime, where all the temperatures are pegged near freezing in the summer because you have ice melt going on. But what's going on aloft is a very different story. And so we had a couple of these warm air intrusion events, both in the summer as well as some happening, I think it's in this cluster, where you get some really strong and much warmer air, strong inversions with much warmer air aloft. So that's one of the things that we're looking at, is how those types of events are impacting the surface energy budget and the formation of clouds, as well as aerosol particles. So there were some studies being done by Swiss teams looking at how aerosol concentrations were changing near the surface in these warm air intrusion and transport events. But again, a really wide variety of different types of conditions. You have cases where you have that well-mixed boundary layer all the way up to the cloud, and other cases where you have elevated inversions and decoupled cloud layers. So a lot to dig into here. I mentioned the leads. We did fly the Data Hawk to try to capture details on the impact of leads on atmospheric structure. And this is something we're just getting into. So I don't have a ton of initial results to show here, but the types of leads we were sampling were relatively small. They were maybe a couple 100 meters across. And I think it's an important question what the impact of these types of leads might be, because the ones that we see from the satellites are often quite large, kilometers across, and we know that there is significant energy transport from the underlying surface into the atmosphere in those instances. But I believe that these smaller leads are much more prevalent and much more frequently occurring. And so there's a kind of scale and number issue to consider. So the profiles on the right-hand side show examples of flight data. We separated the flight profiling between the upwind and downwind portions relative to the lead, which is kind of the green points here. And as I said, we're just digging into this and starting to look at whether we can see any notable impact of a lead of this scale on the overlying atmosphere. So I mentioned the Helix as well. Here's another one of our cartoon characters, our superheroes, also known as the Buzz. Helix is a hexacopter that we developed and built up at the University of Colorado. We worked with collaborators at Kip and Zonen actually to develop kind of drone-specific pyranometers. In this case, these are lighter weight versions of the PR1 that we put on up and downward looking gimbal systems so that we can keep them level in flight. And we did conduct early flights with a fixed wing platform that also carried pyranometers. In that case, it was the Delta T SPN1s. And we found the corrections that we needed to make to be quite challenging. And even though we were doing everything correctly, it was challenging to correct for any small tilt offsets of the sensors. And so we decided, with the evolution of the technology, and especially the battery technology, to now leverage a multi-copter system, which is providing us with roughly the same endurance as the electric fixed wing that we were carrying these sensors with previously, which is about a half hour of time, so that we can keep things a little bit more level in flight with these gimbals. We also had a multi-spectral camera, in this case a MicaSense Red Edge, which has 4 channels of visible image or imagery that we can put together to do feature characterization. And so here are some examples of the data collected by the Helix. I mentioned the subgroup scale variability. Thinking about the surface, the Arctic ice surface is incredibly heterogeneous, and there's a lot going on just from the perspective of the development of ice ponds. And then during the summer season, as these ice ponds are in place, you can have drainage events where a bunch of the ice ponds will get so thin that they drain out, and then you're left again with the bright underlying surface beneath them. You can have refreezing events, you can have precipitation falling on thin ice. And so this sort of a scene that you see in the bottom can change from day to day, depending on the weather conditions. And so we leverage this platform to conduct mapping operations like you see in the bottom left. This albedo map there is associated with the image on the left-hand side. And you can see, of course, the darker surfaces in the center associated with the melt ponds and the variability in albedo. These were collected at about 20 meters. And that altitude actually is quite important, as is shown by the upper figure here. One of the questions we were equally interested in was the impact of aggregation and scales on the albedo measurement that's made. And so this figure in the center shows the upwelling irradiance over 2 different surfaces, a melt pond for kind of the profiles that end on the left, and then the snow profiles that end on the right. And as you gain altitude, you can see that upwelling irradiance changes pretty dramatically until you get to an altitude of about 40 or 50 meters, where things aggregate to a common albedo value for the scales present here and for the field of view of the sensor. And so these questions are interesting from the perspective of putting previous measurements of surface albedo into context, as well as capturing at a much higher resolution the horizontal variability when we fly at extremely low altitudes. And this shows some examples of that. This work is being done by Radiance Calmer, who's a postdoctoral scientist working with us at the University of Colorado. And she's looking at feature identification to try to characterize the scale of different features over the length of the melt season. So specifically melt ponds, bare ice surfaces, dark ocean surfaces, and snow-covered surfaces. And she's also working to document the different types of albedos that were observed over the course of this time period. And so this is an example of one of those very low altitude flights where the aircraft was left to hover above features of interest. So this White Ridge, for example, high albedo, of course, the melt pond has a much lower value, the ocean much lower still. and then document the evolution of that over the different flights for different types of features. This is all very much work in progress. We're happy to collaborate on this stuff with anyone who's interested, but we just got out of the data processing and publication phase for Mosaic, and now we're starting to dig into the science more. All right, very quickly, the last campaign I'll mention is one that we conducted this past spring. This was another instance where our team at the University of Colorado was contacted by another PI who had NSF support and who was interested in getting a clearer picture of what was happening in the lower atmosphere as part of her research. And specifically, this research, which is part of a campaign that was called Wisco Disco, is focused on the impact of nearshore circulation, so lake breezes or land breezes, on ozone concentrations over coastal Wisconsin, because you have high emission sources at the southern end of Lake Michigan in Gary and Chicago, and you get transport of pollutants out over Lake Michigan, and those are left to sit there in a very stable regime in the springtime where the lake water is still quite cold and mix, and the chemistry is definitely not my strong point, but ultimately you get these circulation events where the lake breeze pushes a lot of that pollution inland on the coastal areas. And so our part of that with the Raven was to document the evolution of the lake breeze environment and the structure of that circulation over time while they were flying a multi-copter with ozone sensors to get profiles of the ozone concentrations from the surface up to about 400 feet. And so the bottom figures show a few examples of those flights. On the far left is it's a little bit of a twisted plot. So you have longitude on the x-axis. The black line roughly represents the position of the lakeshore boundary, and then time on the vertical axis. And so, you know, as we progress through the day here, you can see this marine boundary that exists in the nearshore environment, which gradually decays as we're making repeated passes onshore and offshore. And this is actually the flight that I was showing you earlier, flying over the camera, flying over the Wisconsin shoreline, was from this particular day. Looking at it in vertical space, you know, things look a little different. Again, you can see the early presence of that lake breeze circulation, which then is pushed offshore in this particular day and then comes back in the evening. And then just from a vertical profile perspective, this is what things look like. You know, you have the nearshore environment kind of bouncing between that lake breeze and the convective boundary layer from the coastline throughout the day. And you can see huge amounts of variability there in the temperature structure. But it's really these types of events where you do have the lake breeze coming on shore that tend to push ozone concentrations up to levels that are unhealthy for the population. So looking ahead a little bit, we have some upcoming campaigns. Next summer, we're participating in the Tracer campaign. This is a Department of Energy funded project, and we're collaborating with our colleagues at the University of Oklahoma who will be flying their copter sound system. We'll be flying the Raven, and perhaps somewhat similar to the Wisco Disco campaign, our role is really to document the sea breeze and its interaction with the background convective boundary layer, and try to understand the impact of that kind of enhanced lift and the difference in the aerosol properties as well on the development of convection over the greater Houston area. And so we're going to be flying the Raven in South Texas in the summertime to conduct, again, these long profiles across the sea breeze frontal zone and better document how turbulence and aerosol properties may help to enhance convection around that area. I mentioned the superheroes. We've got an active project right now in the Crested Butte area called SPLASH. SPLASH is the study of precipitation, the lower atmosphere, and surface for hydrometeorology. And this is focused on all things that help to drive water into the Colorado River. We have a bunch of surface-based sensors, radars, towers, surface flex stations. The OU clamp system is out there. But then we're also deploying some of our aerial assets, working with the University of Colorado IRIS program and Black Swift, who have a soil moisture mapping system that we're going to deploy to this region as well. We're collaborating with NREL and some other collaborators to begin to develop Raven as a platform that can map out weights associated with wind turbines and better understand how the presence of wind turbines will impact downstream atmospheric state. So that work is still early on, but we have started conducting some flights on the NOAA campus here in Boulder. And we hope to participate in upcoming campaigns in Oklahoma that will target larger wind farms in that area. And then we're always looking to continue to innovate our sensing capabilities. And some examples here, we're currently in the process of developing our own multi-hole pressure probe. This is largely being undertaken by Steve Borenstein at the University of Colorado. And we have a lot of interest in trying to automate some of the sampling. And so this is an example from a French team who they're way out ahead of us on this, but we hope to catch up someday, where they have technology in place to deploy these assets and have them make their own decisions in flight about how to best sample a convective plume, for example. And this, I believe, is a simulation-based version of this, but I saw this firsthand during Atomic, where they would send the aircraft out. It would fly its own flight pattern based on its measurements that it was making, and then it would come back a couple hours later. It's really neat technology, and I think there's a lot that can be done in that area. All right, so I'll summarize quickly. We're using small UAS to provide new perspectives on the lower atmosphere and its interactions with the surface. And we've deployed these assets around the world, from the poles to the tropics, to document kinematic and thermodynamic structure of the lower atmosphere and help improve our understanding of lower atmospheric physics. Currently, we're working to understand the Arctic boundary layer, momentum transport and cumulus development and tropical trades, mountain meteorology as part of SPLASH, the potential impact of these types of observations on local scale numerical weather prediction. And I will say that as part of SPLASH, we've engaged the local weather forecast office in Grand Junction, and they're very excited about the possibility for gaining insight from small UAS. Additionally, we're looking at how local scale circulations may impact weather and air quality, looking at surface properties and trying to work with NCAR to better understand how we might be able to assimilate measurements of those surface properties in high resolution simulations. I mentioned the wind energy work, and then of course, continuing to advance our technology. And I want to end by saying that there are a ton of opportunities out there. We are definitely actively looking for additional collaborators who see potential benefits to integrating UAS into ongoing Earth system research. And so, if any of this looked interesting to you, I strongly encourage you to reach out and maybe start a conversation about how some of these assets might be deployed to answer questions you have on the lower atmosphere. And that is what I have for today. I do have references up. They're in the presentation, and I'm going to put them here so that when the presentation later is recorded and people go back to it, you can see this for a few minutes, but maybe I'll leave it on the summary for the time being as we transition to questions. Thank you.
All right. Well, thank you, Gijs, for the beautiful images and movies of the UAS measurement system and the clever applications through the various campaigns. We do have time for questions. Again, the Slido interface is below the presentation screen. And we do have a few questions, and I'm going to present them in the order in which they have been submitted. And that would be Andrew K. Asked the first question, and he asks, how are wind observations from the UAS delineated from the actual motion of the UAS and the turbulence that it causes?
Yeah, that's a really good question. And so in short, it's done the same way that it's done for large research aircraft. It uses the same types of equations where we have an inertial motion or measurement unit on board, and that measures all of the motions of the aircraft. And the winds aren't directly measured, they're actually derived using the information from the multi-hole pressure probe, which is telling you how the aircraft is moving relative to the airflow around it. The GPS on board, which is giving you the aircraft velocity over the ground, and then the IMU, which is telling you about the pitch, roll, and yaw of the aircraft. And so that's how the winds are actually calculated. The question about the turbulence that the aircraft causes is a different one. And we've been working to try to document that with both simulations. So looking at really high resolution simulations of flow around our platform and trying to understand, what sort of disturbances it may cause in different sampling regimes, as well as in a wind tunnel And that's definitely ongoing work, but we're trying to extend that probe, which would be impacted by any sort of turbulence or flow around the airframe, out ahead of any impacts that the aircraft might cause. Hopefully that answers the question, Andrew, but if not, I'm happy to provide more insight.
Thank you, Andrew. James Pinto, your collaborator and colleague, asks a question. He asks, can you comment a bit more about uncertainties in measurements obtained with UAS?
Yeah, sure. I think this is one of the more challenging things to accurately calculate. We know kind of what our sensor uncertainties are reported to be, but as I mentioned with respect to the lapse rate campaign, a lot of the actual uncertainties with the measurements comes down to how their sensors are integrated onto the platform. And so we've been working, as I mentioned earlier, to do side-by-side comparisons with trusted systems that people have documented to better understand how well we do measure things with the platforms that we're deploying. I know from the perspective of data assimilation, the uncertainties are important. And so I think it's something that we should work on collaboratively and move towards the best ways to document all this, following published techniques in the literature, as well as taking into account some of the specific considerations for these small platforms.
Thank you, James, for that question. We have another question from another colleague and collaborator, Terry Hoke, here at EOL. Gijs, thanks for a great presentation. What do you see as the future for multiple UAS flying simultaneously, like a swarm, a network, to create the concept of a vertical moving tower from both a science need and from a practical implementation of the technology and logistics? Thanks.
Yeah, Terry, thanks. That's a really good question. I think there is a lot of promise for this. And I think that we've certainly operated multiple aircraft at once. I wouldn't call it a swarm. It's usually two. I think maybe at the most it's three. But I do see opportunities to increase those numbers. And I think doing that, some of that comes down to what's practical given the current guidelines and regulations that the FAA has, right? So at the moment, things are set up in a way that for each aircraft, we need a separate pilot and separate observer. And if you start to put 10 or 12 aircraft up at once, that becomes a lot of people, which negates a lot of the cost savings and other benefits that UAS offer. But I think we can move in that direction. And I think that from a scientific perspective, having the ability to capture simultaneous observations at different altitudes or over different environments. And I'll bring up the example of the Lake Michigan study again. We already know that the next time we go back there, we're bringing more than one aircraft, because ideally we want to be able to profile simultaneously, both onshore and offshore, instead of transitioning between the two all the time. And then we can get kind of isolated information over the different surface types and in kind of the marine side and the continental boundary layer side. So I think there's a lot of promise for multiple aircraft operations, and we have to keep moving in that direction and demonstrating to the FAA and others that we can do that safely, and that there's benefit to doing that.
Great question. Thanks, Terry. We have a question from Ned Patton here at M-Cubed, and he asks, perhaps I missed it, but have you characterized the Miniflux observed momentum fluxes as they relate to that observed by other instrumentation, i.e. either the sonics at Marshall or the LiDAR at the San Luis Valley, or similarly with other instrumentation during Atomic or Mosaic?
Yeah, thank you, Ned. That's a very good question as well. So I didn't present on that. I have done some comparisons, not for the momentum fluxes, but for sensible heat fluxes that we calculated from the Raven relative to, trying to remember whether it was the SGP tower or the NREL tower. I can't remember, but we have done some comparisons between those. They generally compare well. I haven't published any of that, so it's still in progress, but yes, it is on our screen to move that forward and document how well we recreate those measurements from the aircraft.
Thank you, Ned. I think we have one final question And this is a question from Matthias Steiner, who is our Director of Aviation Applications Program at RAL. And he says, thank you for a stimulating presentation. It is great to see how far you have come using these platforms to collect atmospheric data in challenging environments. Have you thought of how to deploy UAS platforms in urban landscapes to collect data about wind, turbulence, air quality, or heat island?
Yeah, that's also a really good question. I have thought about these platforms to measure a lot of the things that you mentioned here. Specifically, the heat island and air quality come to mind as kind of critical observational needs in urban environments. And, I'll be honest and say I've been very busy with the other campaigns and haven't dug deeply into how to best do this. But part of me is actually hoping that it will be done for me. And I don't say that from the perspective of being lazy, but I say that from the perspective of kind of the air mobility side that's taking off, and the particularly urban air mobility, which are, delivery platforms, or air taxis, things like this that are started. People are looking into this as viable means for conducting business in the future, and that ranges from Amazon to pizza delivery to people delivery. So if you have these platforms operating in urban landscapes, you no longer have to worry about how to best deploy them. They're already there, and it's just a matter of instrumenting them correctly. And that was actually part of the motivation for Miniflux, although Miniflux is likely too large for that specific application, but was to develop a common package that could be put out there to collect data from platforms of opportunity that are flying already.
Great final question. I see potential area of collaboration there, Gijs.
Of course, yeah.
Well, I see we are past the seminar hour. If you are interested in Dr. Gijs de Boer's presentation and have further questions, please reach out to him via his email, which is provided on the seminar flyer. On behalf of EOL and RAL, I would like to thank Dr. de Boer on his excellent and attractive presentation on UASs. Thank you, everyone, and have a great day.